and DC. And what is rho pi 2? AC, CA, BD, DB, AA, BB, CC, DD, AACA, BD, DB, AA, BB, CC, DD. So all of you can look that these two are what? Equivalences on set X. Equivalences on set X. Try to utilize this. See, they are reflexive and they are symmetric, and they are symmetric also, and also they are transitive, you see. So as well as if you see rho pi 2, again it is transitive also, as well as symmetric also, as well as reflexive also. So both are equivalence relation on set X. Now if we talk about the union of these two, that is rho pi 1 union rho pi 2, if we discuss about this, then what happens? So if you talk about, you can calculate well what is, because it contains the elements of both, no problem. Now this, you see the union is if you discuss about this, you see that it is not transitive. Why? Because A comma B as well as B comma D both belongs to this, but A comma D does not belongs to rho pi 1 union rho pi 2. It means that rho pi 1 union rho pi 2 is not equivalence relation. So what we have seen that union of two equivalences need not be equivalence in general. A comma B as well as B comma D both belongs, but A comma D does not belongs. It means what? It means that it is not equivalence relation. So this is one example. Also I want to discuss another example. I will like to left for all of you that one, because that example maybe it is problem. Let me see. Okay, see proposition 1.4.7, the last result of this lecture. If phi from X to Y is a map, then then phi or phi inverse defined as x comma y belonging to x cross x such that x phi is equal to y phi also. Before that they have written like this. And there exists z belongs to x, x comma z belongs to phi, and y comma z belongs to phi. This is equal to the set x comma y belonging to x cross x such that x phi is equal to y phi. Then we have to prove that then phi or phi inverse is equivalence on set X. We have to prove that this relation is an equivalence on set X. And such a set is called, it is called kernel of phi. Kernel of phi. Kernel of phi is equal to phi or phi inverse x comma y belonging to x cross x, such that of course when x comma y belonging to, how these sets are equal to each other. Of course when x comma y belongs to phi or phi inverse, then there exists some z such that x comma z belongs to phi, and z comma y belonging to phi inverse. When z comma y belonging to phi converse, and of course phi y comma z belongs to phi. So x comma z belongs to phi and y comma z belongs to phi is okay, right from the definition of composition of two functions relations, of course. So and as they are maps, you see, as they are maps, so from here you see, from here x comma z belongs to phi, it means that z is equal to x phi, and of course z is equal to y phi. So they have written like this. So both are equivalent to each other, it's obvious. Why? Because phi is what? Phi is a map. Phi is a map. It is given phi is a map. So phi composition, phi inverse is x comma y belonging to x cross x. That is also called kernel of phi, such that x phi is equal to y phi. We have to prove that this is equivalence. I think it's trivial, because you see that x phi is equal to x phi, it implies what? X phi is equal to x phi, it implies what? X comma x belongs to kernel phi. And when x phi is equal to y phi, you see, when x comma y belonging to kernel phi, it implies that x phi is equal to y phi. X phi is equal to y phi or y phi is equal to x phi, both are same. It implies that y comma x belongs to kernel phi. That is, phi is what? Symmetric. Now if x comma y belonging to kernel phi, and also you just write like this, x comma y as well as y comma z belongs to kernel phi, it implies that x phi is equal to y phi and y phi is equal to z phi. So when x phi is equal to y phi and y phi is equal to z phi, so it implies x phi is equal to z phi, and it implies that x comma z belongs to kernel phi. So kernel phi is reflexive, symmetric, transitive, so hence it is equivalence relation on a set X. But phi should be what? It should be a map. They are already told that phi is a map from X to Y. Then this is true. So this is all about today's lecture. This is lecture number 11 going on. So today I have given two lectures, lecture 10 as well as lecture 11, and so we stop here. Thanks.